This is a gas with lots of molecules, all of which have kinetic energy, so they're moving around. And if we just leave our gas, all those molecules are going to move away and they're going to escape, and we're going to lose our gas. So we're going to put our gas into a sealed box. Now, the molecules are all still moving around, depending on how much energy they have, of course. And as a result, they're going to hit the walls of the container and bounce off. And so they are going to exert a force, and therefore a pressure, on the walls of the container. If they are exerting 1 atmosphere of pressure, that is 101.3 kilopascals. Now let's say this gas is a mixture of oxygen and nitrogen, and it's a 50-50 mixture. So half of these molecules are oxygen molecules and half of them are nitrogen. Therefore, half of the pressure is exerted by the oxygen and half of it is exerted by the nitrogen. So we say the partial pressure of oxygen is 50 kilopascals and a little bit more to make it up to 101.3, and the partial pressure of nitrogen is also 50 kilopascals. That's what we mean by partial pressure, is what part of the overall pressure is made up by the gas in question. And this brings us to Dalton's law, which is the partial pressure of the first gas plus the partial pressure of the second gas, and so on, will sum to the total pressure of the gas mixture. That is Dalton's law, and it's fairly intuitive. Now let's take our box of gas molecules and let's heat it up. We're going to give more kinetic energy to the molecules inside, because if we've got these molecules moving faster, then if we keep the volume of the box the same, these molecules are going to have a lot more energy, they're going to bounce around more, and the pressure is going to increase. Therefore, if the volume stays the same, and we increase the temperature, the pressure is going to increase. This is Gay-Lussac's law. And Gay-Lussac's law tells us that at a given volume, the pressure of a gas is proportional to its temperature. And this can also be expressed as P over T equals a constant. Now remember, the volume is staying the same, and we're changing the pressure or the temperature and seeing how the other one reacts. And Charles's law states that at a given pressure, the temperature of a gas is proportional to the volume it occupies, or volume over temperature is a constant. So for Charles's law, I find it easier, instead of a box, to have a balloon. And basically we're going to take this balloon and we're going to put it in the fridge, and what's going to happen is it's going to shrink. And what we're saying is the balloon's elasticity, we're going to assume, is applying the same inwards force against the outwards force of the molecules. So we're going to say that the pressure has remained constant, and what we've done is we've reduced the temperature and the volume has decreased. That is Charles's law. If you keep the pressure the same and change the temperature, the volume will change as well. And finally, we have Boyle's law. And Boyle's law states that at a given temperature, the pressure is inversely proportional to the volume, which makes sense because if I compress this volume down and make it much, much smaller, and I keep the temperature the same, then the pressure of that gas is going to increase. Likewise, if I make the volume bigger, the pressure is going to decrease. Now remember, this is the only one of the three that is an inverse relationship. Both the others are proportional. If the volume increases, the temperature increases. If the pressure increases, the temperature increases. But Boyle's law is an inverse relationship, and that's often where people get caught out. And it states that at a given temperature, then the volume and the pressure are inversely related. And the final thing you need to know for the exam is that these three all combine into the universal or ideal gas law. This is the ideal gas law, and all you need to be able to say is that it is PV is nRT. Pressure times volume equals N, which is a constant to make the numbers all work. R is the ideal gas constant, which is about 8.31, and T is temperature. If you can just recite that, you don't have to understand why it's that, and the explanation of why R is 8.31 is beyond the scope of the exam. You just need to remember that the ideal gas law is PV equals nRT, and it's a combination of those three gas laws and how they all interrelate to explain how pressure, temperature, and volume all interact in an ideal gas. And all of this can be found in our primary FRCA toolkit, which is outlined in Viva format that you might get asked in the SOE of the primary. It's mapped to the syllabus, and we've got our summary diagrams in there for you. So go and check it out. You can try it for free. If you don't like it and you don't get on with it for any reason, we'll refund you completely, and you can try it out, no risk at all.